All right. Come on in, sit down. Welcome back. So today we're going to, come on in, plenty of seats down here. Today we're going to pick up and diving into the details and starting to go on to a topic of synchronization, which is probably one of the most interesting and challenging ones you'll run across in this class. But before we do that, let's briefly remember what we did last time. We talked a bit about the life cycle of an actual process, which is surprisingly well mirrored also by threads. But basically, the process goes through a series of state transitions. You first make a new one. That process gets admitted into the system onto the ready queue. And when something's on the ready queue, it's not actually running, but it's ready to run. And then, of course, at some point, the scheduler pulls it off the ready queue, puts it on the running queue, and now it's actually got a CPU. And if there's only one CPU, there's only one process or thread that's actually running. Okay, so there's only one thing in this state per CPU. So in a multi-core, you can have multiple of them. There might be interrupts, which will take you, like a timer interrupt, take you back to the ready queue. And so on. You sort of run for a while going back and forth. Eventually, you might try to do some I.O., at which point you're going to end up waiting for some device. So maybe you do a disk I.O. or something, you end up waiting for the disk I.O., and then eventually that completes, you go back to the ready queue, and then you get to run for a while. Then finally, you exit. And there's many ways of exiting. That you can be sent a kill signal, you can execute an exit command, you can return from the main function. There's lots of ways of exiting. And then finally, you go into the terminated state, and you'll stay there until what? I saw this actually, somebody posted a question about this on Piazza. How long do you stay in the terminated state? Forever? Anybody remember? Until what? Yeah, until the parent executes a wait and asks you for your return value. Okay? Now, there's some ways that parents asking for return values can happen under the covers, but essentially it's got to stay there until the exit code is available to a parent. Okay. Are any questions on that? Okay. So then we talked about threads. And we talked about this, which is a use of threads where you can have two things running in parallel, the compute pi to the last digit program and the print class list program. And because you've got threads, now at least you'll see some of the print class list happen. And notice the way I've expressed this is it's all in the same process, but there are two threads. How do I know that? Well, it's one main function, okay? And so what does thread fork do? Well, thread fork goes by many names and many syntaxes, but roughly speaking, it creates an independent thread, and it's usually given some function and some arguments for that function. And what's the behavior? The behavior is you actually see the class list. Okay, and this will interleave things. Were there any questions on that? Oops. Okay, so the basic abstraction here of threads is an interesting one. It's one of our first sort of infinite resource kind of abstractions. We're going to run into a lot of these over the term, but the idea is the programmer just happily keeps creating threads. And as far as the programmer knows, there's, as many processors as you have threads. Now, in reality, of course, there aren't. There's a finite number of processors, like 1 or 2. And as a result, if you create a huge number of threads, pretty soon what happens is this multiplexing that you see here starts to catch up with you, and ends up being more overhead than actual computation. And so while this programming abstraction might be convenient, you better be careful and keep some handle on physical reality. Okay, and as you start to write threaded code, you're going to start to get a better flavor for that, and there is sort of there's a balance of threads that you want to try to keep such that you're keeping all your I.O. devices busy, you're keeping your people sitting at the graphical user interface happy, etc. But you don't want any more than that. Okay. Questions on that? Now, one last thing I did, I realized I was quickly zipping through the stack last time, and there were some things I probably should have said just to be absolutely clear. So what we had on the left here is 3 procedures, A, B, and C. Procedure A at the very bottom gets called with a 1, and that starts a whole chain of things. What you see on the right is the actual stack for this. I'm using the standard convention where the stack pointer is growing down. So the way you interpret this is the high address, this diagram, the high address is up high and the stack pointer is growing down. It's going to be confusing because different people go different directions, and in fact I do sometimes too, but in this particular one the stack pointer started at the top here with nothing, and as it grows you add things going down. And what actually happens here? Well, you call A with a parameter of 1. So part of the knowledge of what happens on the stack, this is what I didn't really say enough of, is it depends on what the calling sequence is for the particular language, compiler, and operating system you happen to be using. Now, actually, more important is typically the operating system, but basically what you're seeing here is that A gets called with a first parameter of 1. What happens in most calling sequences you're going to encounter is that actually gets pushed onto the stack, this first parameter of 1, because the TMP variable gets pushed on the stack, and the return address, which in this case is exit the procedure, because there's nothing after A of 1, gets pushed on the stack, and then A gets called. That's the sequence here. Okay, and if you call A multiple times over and over again, each call of A will have a different stack frame entry. So when we call A of 1, that starts running here, that calls B, and the only thing B pushes on there is the return address. And this is a little funny way to say what the return address is. What I meant here was that whatever the start of A plus 2 is kind of where we return when B is done, and so on. And so each call, B calls C, that pushes a return address on, C calls A, and so on. This particular code does what? Does it ever exit? Why does it exit? Yeah, well, eventually I call A of 2. A of 2 says, is temp less than 2? No, so I just exit with a printf. So this is not an infinitely growing stack. But what happens once I call A of 2 here is it runs through this, does the printf, which will put other stack things on. But when printf is done, we pop the stack to figure out that A has to return back to this part of C, which tells us we got to return from C, which will pop the stack. That tells us we return from B, which will pop the stack. That tells us we return from A, where we return to here. After B, we do our last printf, we pop the stack, and we exit. That's the way this stack is going to happen. So it kind of moves down and up as we do our execution. So I just wanted to make sure that was crystal clear to everybody because the stack is such a crucial aspect of how scheduling works. Were there any other questions on this? Now notice that what I didn't say is, well, when I call C or whatever, what else do I push on the stack? Well, I have to save a bunch of temporary register values as well, and that's where things like calling sequences come into play. Now, 61C used to talk about MIPS. Do they talk x86 now, or do they still x86? Ooh, they make it complicated for you. Well, let me just show you MIPS here for a second. But if you notice, MIPS has 32 registers. Okay? MIPS has 32 registers, and those registers are always in play when you're executing, and those registers are part of a calling sequence specification. And that calling sequence specification says that certain of these are called caller saves registers. Those are the ones I've got marked in red. Certain are called callee saves registers. And so what does that mean? Well, that means before you call a procedure, you've got to save all of the caller save registers. I'm the caller. I've got to save those. I've got to save a couple of other things which might be part of the spec. I've got to save a return address and so on. This is what the compiler has to do. So the compiler gets this spec, and as long as everybody adheres to this spec, chaos does not ensue when you link things together. Okay, and what does it mean that the caller saves registers? Why is that? What does that free up the procedure I'm calling to do? Yeah. Well, not only call other procedures, I heard it down here. Before we do that, what else does it let it do? Yeah. So it says if I save T0 through T7 and T8 and T9 first, and then I call, it can bash those registers any way it wants because I've already saved them. And so when I come back, there's no expectation that the caller saves registers are still there. The call E saves registers, the expectation is they are there. So if that procedure is going to screw them up, it's got to push them on the stack and do the right thing. Okay? That's all part of the calling sequence. And we don't, the details here don't vary basically from operating system to operating system and processor to processor and so on, but you got to know there is a calling sequence. And that dictates basically how the compiler manages the stack. Okay, I'm not going to say any more about that unless people have questions. That make sense? Okay, and there's a calling sequence for x86. Similar things. Certain registers have to be saved, certain ones don't, so on and so forth. Okay? Now, then I pulled up this last time, and I thought we'd go through it again, because this is what I like to think of as the simple way of seeing what's going on. You can do it with actual code, which I will show you. There's other ways I'll show you the same thing a little later in the lecture, but it's starting to get a handle on this. So notice that what we're saying is the following. Imagine two threads, S and T. Imagine they've been running for a long time. Did everybody hear what I just said? Imagine they've been running for a long time. All we're going to do is switch back and forth between S and T, and furthermore, we don't have a timer. The only way that we switch between S and T is with a yield. Okay, so what happens? Thread S, let's say it's running for a while. It says, I'm going to run A, which I'm going to call A, which is going to call B, which is going to eventually call yield. And what does yield do? Yield goes into the kernel. That's what red means. Calls run new thread, which is basically a part of the scheduler that says, this guy is yielded. Pull the next guy off the ready queue. Run new thread calls switch. Okay, and what switch does is switches the registers from thread S to thread T. Okay, and what does that mean? It says it saves all of S's registers, including the stack pointer. It loads all of T's registers, including the stack pointer. And the moment that switch loads all of T's registers, including the stack pointer, suddenly we're in the context of T, not of S. It's as simple or as complicated as that. Okay, and now what's amusing about this is while S, call, switch, normally you return from switch, you return from run new thread, you return from yield, you work your way back up the stack, except I switched the stack. And so when I return, suddenly I'm returning up through T. Okay? So that's what happens when you manipulate the stack pointer. It changes the context. Okay, and I go call, return. Well, wait a minute, I'm returning somewhere else. Why? I have a different stack. And T will go through the same process, call yield, back up to S, and so on. So we're going to seesaw back and forth here. Okay? Are there questions? Now, I'm sure the answer to that is yes. Because this is a little weird the first time you see it. Maybe this is the second time, therefore it's no longer weird. Yeah, go ahead. So where is it returning to? Well, it's returning to, first of all, it is returning to the same address because it's the same code, because it's the same thread, except I'm in the context of T now because it's T's stack. So I'm moving up and down this data structure, which is T's stack, rather than this one, which is S's stack. That's right. So if T was running some completely different code, when I return, I'll still return from switch and run new thread, but then when I return, I'll return into T's code wherever it came from into yield. Yes. Okay, so you're right. This is a little bit weird because it's an identical code, but which is either good or bad depending on how you look at it, right? Okay, good. Yeah.
So, is there a difference between the register to yield and the return? What if, for example, after the second yield, if T adds a different code where it returns, it calls return as opposed to calling yield?
So return is something that you get out of a procedure with, whereas yield is just a procedure, the way I've shown you here. So when I call yield, that's really in the C library, and yield, it's just a function call, and so I'm returning from that function call from yield. All right, but yield then makes a system call, which is a type of function call that happens to change modes and so on in the kernel, that changes stacks in the kernel. But they're all system calls at some level. Good. Yeah.
We have code to execute after the yield.
Yes.
Does it never get executed?
Oh, sure. Good question. So here we go. While true, yield. Compute the square root of 5, whatever. Yeah, what happens? Yield just says, give my processor time quanta over, put me on the ready queue. Later, I get taken off the ready queue. Somebody else switches to me. I return out a switch. I return out a run new thread. I return out a yield, and poof, I start computing the square root of whatever. So yeah, I just returned from yield, but I returned from yield later. It's like I went to yield, something happened, I returned from yield. I keep going. Good question. I mean, this is either a great simple example or too simple, but basically what happens here is I return from yield and then I go into my while loop and, do the next loop and yield again, which is a little why it's a little confusing. But technically speaking, I'd come out of yield and I'd compute the next thing after yield if there was something. Good, yeah.
So the only difference between this and actual, the different processes is that this is using essentially the same stack set different.
No, different stack, same address space. So if this switch was switched between processes, which is essentially the same idea, I would not only be switching all the registers out, but I would be changing the memory state. I'd change the address mapping hardware. Same idea otherwise. But now that's even more weird to think about because suddenly I'm in a completely different address space and I'm returning up of a different stack, right? But that's why I don't bring it up right away, but it's the same idea. Essentially the same idea. Okay. I have a wonderful quote, by the way, I'm going to show you guys from Dennis Ritchie later that I found. It's just fabulous, just about this very topic. You'll love this. Any other questions? Okay. So now, remember I mentioned interrupts? So we're busy executing some assembly code, we have an interrupt comes in, maybe the pipeline flushes, we save our program counter, disable interrupts, and so on. We run the interrupt handler, we restore the PC, we come back. So the essential idea here of an interrupt was stop what you're doing, go off, manipulate the interrupt state, do what you're supposed to do, restore the state, come back, and continue. And the guy on the left, which is a piece of user code computing the last digit of pi, of course, that's what we compute, right, doesn't ever actually notice that the interrupt happened other than there's a little bubble in there. Okay, that's the important part of an interrupt. And what about that interrupt? Well, that interrupt here, I'm saying it's a network interrupt, but it could be a timer interrupt. And the timer interrupt is going to do something for us. Like, for instance, it could return control to actually do the switching that we mentioned earlier. So we're busy running. The interrupt happens, which again ends up looking like a procedure call onto the kernel stack, which then maybe calls run new thread and switch. And poof, we're overrunning T now instead of S. So the only thing I did that's different here from before was I put an interrupt in there, and the interrupt effectively called yield. I don't want to quite say it that way, but it kind of did the same thing that yield does, and it called the scheduler, and the scheduler picked a new thread, and now we're back scheduling something else. And this is how timers get involved here. Okay? And remember, the red thing here is kernel stack, kind of, and the blue thing is user stack. So I want you to keep track of the fact that in the kernel we have a different stack than the user. Okay. All right. And then, of course, how the heck do you even start a thread? Because every thread that Professor Kubatowicz ever has put up so far has been running forever because it's computing pi. What's great is I can make a dummy stack segment that looks like there was something running there that I can return into, and the act of returning into it starts the thread. Okay, so here we are running the other thread. It calls yield. We call run new thread and switch. That switches to this, which is not quite inside of switch, but it is inside of some other procedure, and the act of going into it causes the thread to get started. All right, and what does it look like? Well, maybe here's an example of what it could be: some sort of housekeeping, switch into user mode, call a function, which is the thread function, and then finish. All right, and what's the housekeeping? All sorts of stuff you could imagine, like keeping statistics. Thread root, basically I can set up the initial frame so that the return, when I return to it, actually returns me to the first instruction of do startup housekeeping. So that very first time switch returns to the thread root and starts it up, what do? I start executing at the beginning of this. I do a user mode switch. I call a function pointer and so on. And now that thread is just plain running. Okay? So if you like to take this view that what I'm going to do is I'm going to set up my stack frame such that when I go to it and start running at that point, it's as if I'm actually, I can return into it and things just work. And it's the same place as when I executed that switch procedure call, then you're good to go. And most of all of the thread manipulations that you do in the kernel can be looked at this way, assuming you've got a kernel stack that you can put into the right format. All right. Now, so I'm going to pause. Do we all have this? This is the core idea, actually, behind a lot of thread switching algorithms. Okay, so what can we do with multi-threaded programs? I just wanted to say multiple threads are everywhere. You could use them in embedded systems, elevators, planes, medical systems. You can use them in modern kernels, obviously, which is where we're using them. They can be in database servers. So multiple threads inside of a program, basically everywhere. And I'm going to show you in a moment. It's kind of amusing, but things like network servers, you could have a thread per flow, right? Every flow going through your network server basically has a different thread on it. Or you build a router, each one has a different thread. Basically, you can use multiple threads when you have multiple processors to do parallel computation. That's going to be an interesting way to compute, okay? And presumably in the 61 series somewhere, they've started to make you guys look at multi-threaded programming, right? This isn't the first time you've seen it. Okay, this is the closest you've gotten to the threads. Okay, I think you've used them as an abstraction. And then, of course, basically multiprocessors are basically sometimes people use them in a rather silly way where each processor is doing its own thing and you have multiple threads just because you have one per processor or whatever. Okay. So here's a typical use case that you do every day. You have a browser with a client, a web browser, and a web server. The client typically often has one thread per connection, and sometimes you can have more than one connection to a web server. So that little diagram I showed you where you connect with the server and it gives you a unique connection, you can have several of those open at once. Think about a web browser where the pictures are loading in parallel or whatever. Okay, and the web server can basically have many people talking to it, and so there's lots of things like we can have a process for each client, a thread to get the request and issue responses, and so on. So multi-threaded programming is everywhere. And what you hopefully are going to start to worry a little bit about is how do we manage this chaos and make sure it all works? Okay, because as soon as we start having threads in the same address space touching the same data structures, now we've got synchronization disasters that are just waiting to happen. Okay. So here's some actual numbers. So for instance, you go, if you're, here you got a Windows box and you pull up the Windows Task Manager and you ask it to actually display threads. You have to configure it to do that, and voila, look at this. Thunderbird, 28 threads. Firefox, 49 threads. Okay? So these things are multi-threaded. Okay, you ought to try that on your laptop sometime. Lots of threads. I'm actually not a Mac person, so I don't know the equivalent, but I'm sure the Mac has an easy way to show how many threads a given process has too. So multi-threaded is kind of the name of the game. I think the first time I ever saw this, though, I was a little bit in shock that a Firefox browser may have 49 threads in it. You know, that's a lot of threads. But when you start thinking about, well, you have lots of tabs and you got lots of things going on simultaneously and you got background tasks doing synchronization of the you know, my bookmarks and all sorts of weird stuff going on there, then you can see where the threads add up. Okay. So use cases in the kernel, lots of them. Thread for every user process, thread for sequence of steps in I/O, threads for device drivers, ... The kernel has got threads everywhere too. Now, what's interesting about this, by the way, is it didn't used to be that way. Not too long ago, and when I say not too long ago, I'm not talking 50 years, I'm talking 10, maybe 12. It was the case that OSs were essentially pretty single-threaded, so that there was only one thing that was a process that was allowed to be in the kernel in a system call at once. So you had lots of user programs, they're all running in parallel, but as soon as one made a system call, it essentially locked out everybody else from doing system calls. And this was a pretty common way to build kernels up until multi-core became really prevalent, and basically parallelism was everywhere. And you can see very quickly what's wrong with that scheme once you have lots of processors. What starts happening? Yeah. Well, different memory and address spaces, kernels did pretty well with that. No, that's not the problem. Yeah. Yeah, you got lots of things actually running in parallel, and you know, one of them goes into the kernel, and now the next one that wants to go in the kernel is stuck. You know, there used to be a big kernel lock, you know, do not enter. Somebody else is here. Okay, and that was the big problem. And so it was really, you know, it took a re-architecting of a lot of kernels to get to where we could have threads in the kernel, and that was a big deal 15 years ago, 12 years ago. So, okay, so administrivia. Group formation, I understand, should be completed essentially tonight with stragglers. Is there anybody who has not contacted the TAs about groups? Good. Okay, if you don't have a group, you better talk to the TAs now because you got to have a group. All right? There was actually a posting on Piazza just a couple hours ago about this, so make sure that you look. The other thing is project number 1 is essentially released. Dun-dun-dun-dum. And so technically it starts today. I understand, although maybe this has been updated in the last couple hours, the AutoGrader's not there quite yet. I think it'll be up there by tomorrow, or it's almost ready for release. So that kind of goes up with not quite there yet, but it will be by tomorrow, I think, right? Good. So those of you that want to get everything done tonight and do the AutoGrader, you have to wait till tomorrow. Homework number 1 is due today, of course. Oh, did we move it?
Yeah, we pushed it back a week.
Oh, we did. Oh. See now. Ta-da. We pushed it back. Okay, good. It's actually due. Dun, ta-da. Yeah, I thought it was true, so I'm glad we finally decided to do that. Due next Monday. Good. Let's clap for the TAs. Yay. Good. The one thing I did want to point out about submission is at homework 0, we had a couple of stragglers that hadn't figured out how to get working and they couldn't push to the master branch and so on. We're not letting you do that for homework 1. So homework 1, you got to do the normal submission. Okay, so homework 1, you got to submit exactly the way it says in homework 1. And if you're having trouble with that, talk to your TA. And I'd say do it in the next week. Okay? Are there any questions of administrivia? That's good we pushed that homework. It was a little long. Okay. So I wanted to put this quote up. This is great. So here's a piece of code from Dennis Ritchie. Does anybody know who Dennis Ritchie is? Yes? Well, he's he's the R of K and R. That's right. And so Richie's one of the two people that invented C. And here is some code that you can look up in the scheduler for Unix v6. And I've quoted it for you. If the new process paused because it was swapped out, set the stack level to the last call to savu, that's u_ssav. This means that the return, which was executed immediately after the call to aretu, actually returns from the last routine, which did the savu. Quote, you are not expected to understand this. Now, I think the fact that that was actually in the comments is very amusing. I would say you might want to assume that your comments are a little bit more understandable than that. But it does say that this little thing that we were talking about with the stacks is a little bit obscure, requires some pondering. Okay? You sit down with a good cup of coffee and you ponder, or a good beer, or better, a good wine. Well, whatever. You sit down and you ponder this because it is a hard concept. And so it's okay to be hard. Okay? So that's my quote for the day. I thought that was pretty funny. This is actually in some code. Okay. So where are we now? So we put everything we've been talking about together. We get a process. So what's a Unix process again? It is code, running code, because it's got its own chunk of memory, it's got a stack, it's got some I/O state like file, socket, context, etc., file descriptors. It's got some CPU state when it's not running, like registers and stack pointers and all that sort of stuff. These are resources here, memory, I/O states, that get duplicated potentially when you fork. Okay, and that includes the stack. When you do a fork, you get a new stack it's identical. Why? Because you're in the middle of the same procedure and you need to call and return and so on, right? So the resources, I/O state, file descriptors, these all get duplicated. We have our sequential stream of instructions, and then we have state, program counter, stack pointer, registers, other things which are stored in the operating system when this particular process is on the ready queue and not running. Okay? That's a process. Now, this is not a particularly amazing process, because this particular one, how many threads does it have? One. How do I know that? I see one stack. Okay, if I have more than one thread with one stack, I know I've got a mess. Okay? Now, so that leads, of course, to lots of processes. Okay, and we can put lots of processes on a single CPU. And when we do that, we end up with a situation where we've got parallelism. The switch overhead's a little high because I've got to switch out address spaces every time I switch. The state is not a lot of state. It's low. The memory I/O state's kind of high because the way I constructed all of these processes was I did fork, which does a lot of duplication of memory. Okay, so the memory overhead's high. Now, by the way, for those of you that say that's just... How many people saw exec and said, boy, fork is a really stupid way to create a new process? Did anybody? There's at least one person. Why? You duplicate a lot of stuff and then you throw it out. Yeah, that sounds like a really high-quality way of doing things. Don't worry. In fact, what actually happens is when you do a fork, what really happens is they don't duplicate all the state. What they duplicate is the page table pointers. So all the state stays the same, and we have pointers which are all set at read-only. It's called copy on write, and the moment anybody does a write, then we copy state. So what actually happens when you fork is you duplicate page table entries, which is a much cheaper operation, and then you throw the page table entries out. Okay, so I just saved a lot of you from sleepless nights, I can tell. So process creation here is a little bit on the high side, though, because we got to go through and do some work, all right? Is there protection? Yes, the CPU is protected, the memory is protected. Every parallel piece of code that's running is protected from every other parallel piece of code, so that's nice. Sharing, harder. If I want a process to share with another process, I've either got to do some sort of communication, and by the way, setting up a socket between the two of them and talking between sockets, that works pretty well. Better is actually what's called shared memory, where I have a chunk of memory that's mapped into two different processes, but that's still got to be set up. And so the sharing overhead here is a little tricky with processes. It's doable. Okay. Now, if we put threads in here, what's interesting is now we have processes with threads in them, and notice how we've got duplicate CPU state, we've also got duplicate stacks. We still only have one thread running at a time, but now the switch overhead between threads is much simpler because we're not changing the memory context state. The thread creation is much lower because we don't have to create a brand new process. We just have to create this little bit of CPU state and say, voila, it's a thread. You got to get a little bit of stack space. You set up one of these thread root things. You put it on a run queue, and poof, it exists. Okay. The protection, well, the CPU state in general is protected from other things, but memory and I/O is not protected among threads. Now, I said that a little bit strangely. I will say that between threads, the CPU state is kind of protected, but not really. Okay? Threads can bash each other's stacks, and therefore it's hard to say whether they're actually protected from one another. Memory is definitely not protected because the threads are sharing memory, which means, of course, that sharing is easy. Okay? So the downside of sharing memory is you're sharing memory. The upside of sharing memory is you're sharing memory. Okay? I like to leave you with some profound thoughts every now and then. So you can start to see the trade-offs between using processes and threads. With the threads, we can actually set up and pass pointers to things back and forth, and it works very well. Okay. So now, let's throw in another little wrinkle. So we've been talking about which is essentially what people will call kernel-level threads. Kernel-level threads are threads that are multiplexed by the kernel. So in order to switch from one thread to another, you actually have to make a system call into the kernel, switch the context state, and then come back out of the kernel. So there is a the interrupt has to change modes into the kernel or whatever, and that can get a little bit more expensive than maybe something even simpler, which is to never go in the kernel. Okay? So the alternative here is basically what's often called user mode threads, or user threads. And so this is something I wanted to point out. So the user program itself provides its own thread scheduler and thread package. So all of that stuff I told you about, where we go into the kernel and do yield and switch and come back out of the kernel, we can do that at the user level without ever going into the kernel if we want. Now we've got a user mode thread. Okay, so there would be no red stacks anywhere in that little bouncing back and forth. It would be all blue. And yield is kind of the name of the game there, where I yield, that'll actually make a procedure call which will unload the registers into some local structures and load other registers and start a new thread. Okay? So that's a user thread. And you can imagine that's the cheapest option because we don't even have to go into the kernel to switch back and forth. And the downside of, unfortunately, is exactly that. So if I have 50 threads all run at user level with no kernel interaction, when one of them goes ahead and makes a system call and goes to sleep because it's waiting for the disk, poof, all of them are dead. Because that one thread is the only user thread as far as the kernel is concerned. It went to sleep in the kernel, and all the other threads are never going to run. Yeah?
Would it be accurate to say that user mode threads cannot do load sharing across different CPUs, or have to be running the same?
So I would say it's not quite accurate to say that user mode threads can't go across CPUs because you can set it up where a process spans multiple CPUs. And then there is some possibility that each CPU has got its own kernel-supported thread, and then those kernel-supported threads are all running at user level and exchanging state back and forth. So you can do what you want if you have more than one processor. But you still have the problem that every time one of those threads goes into the kernel, you just lost some of your parallelism. Okay? Now, by the way, if you look at the old book, they definitely talk about this, and I'm sure that the new one must too. Sorry, I put this up and didn't actually check in the book, but there's this idea of scheduler activations, which is a pretty useful fix around all of this, which is that the kernel knows that you're doing user-level scheduling, and when the kernel goes to sleep, or knows it's going to put a thread to sleep from an I/O operation, what it does is it gives another thread, wakes up another thread, and goes back to the user level. And that's called a scheduler activation because you're activating the user-level scheduler based on the kernel knowing that that other thread was going to go to sleep. And so there's a lot of work that was done on scheduler activations to sort of integrate with user-level threads. Okay. You should look that up. It's probably worth looking up. But here's some threading models supported by what I just showed you here. So the simple idea here is basically every user thread has a kernel thread associated with it. Kernel threads are threads that are being multiplexed by the kernel. User threads kind of run on behalf of those kernel threads. And this is really the model we've been talking about. In your mind, when we've been talking, it's really that, yeah, there's kind of a kernel and user thread association one-to-one, and every thread basically gets scheduled entirely by the kernel. These other ones are kind of interesting. So the one I just told you about is all this stuff's running at user level, but there's only one kernel thread supporting you. The moment any of these threads goes to sleep in the kernel, this kernel thread goes to sleep and you've just lost all your threads. This other idea where I have a few more kernel threads, which is sort of natively supported in a multiprocessor environment, gives you a little more flexibility there. This idea of scheduler activations is, well, when one kernel thread goes to sleep, you sort of create a new kernel thread and pop it up to activate a scheduler activation. Okay? Yeah? So, you mean this top one? Here. Yeah, what about it now?
The left side, but
Oh, here.
yeah, so there's multiple user threads, right? If the user, like, if there's a switch between those user threads, does nothing happen in the kernel? Like, what happens?
Yeah, so that's the interesting thing here. So from the standpoint of the kernel, it's just running a program. The fact that that program is giving the programmer this abstraction of threads, and those threads kind of yield to other threads and so on, as far as the kernel's concerned, it's just running a program. And the fact that that program is giving the abstraction to somebody else of threads and is sort of saving and restoring its registers, that's completely opaque to the kernel. And that's kind of the problem that yields scheduler activations as a solution. Is the problem is the kernel doesn't know what's going on. So most, by the way, so we have lots of user-level threads. So early Java was a user-level library with single-threaded process in the kernel, and all of the threading that you're used to was happening at user level. There was something called green threads for a long time, which was a user-level library. Once again, that's like that many user-level threads to one. Windows has a scheduler activation version of this that you can go after. Linux is kind of an interesting, and some of the more recent variants of operating systems is kind of an interesting alternative to this in that in Linux, the threads are mostly these days all running out of the kernel, but they've so stripped everything down to try to make it really fast. Okay, and so when you do a fork, you really make a decision inside the library whether you actually are copying everything or essentially making a new thread. These are all options that Linux gives you, but all the scheduling kind of happens inside the kernel. So, all right, I don't want to go into that too much more detail. Yeah, go ahead.
We're on a lot of threads at the user level.
Yep.
Just one kernel thread.
Yep.
Can we possibly spread them out onto a process?
So the problem, that's a good question. So we have lots of users. So if you want to say this, we've got this guy in the lower left, and we've got lots of threads, but lots of user threads, one kernel thread. Can we spread them out? And the answer is probably not, because this kernel thread really represents a single CPU's worth of execution instructions. And so you really are going to want to have one kernel thread per CPU at least in order to get parallelism out of it. Okay, that's a good question though. Okay, so putting this all together is now we have, suppose we have multiple cores with multiple multi-threaded processes, so that's kind of what I just said here. So now the switching overhead here is really low because maybe they're running actually in parallel and you don't even have to switch them. All right, creation may be low because we're just starting up another CPU. Protection between the CPU, yes. Thread protection, no. Sharing overhead really low, and in fact, you could probably write on one CPU and read on the other one without ever having any context switching involved, so that can be very fast. And we might have 4 threads at a time on a 4-core processor. And of course, I mentioned hyper-threading, where each core has multiple threads in hardware in the same pipeline, and so now we could have a 4-core processor with 2 hyperthreads per core, and now we effectively have what looks like 8 threads at a time running on a 4-core processor. Okay? And does everybody remember? So hyperthreading is Intel's word for it. What's the real word? Simultaneous multi-threading. Okay, that's the word from University of Washington way back when, and Intel called it hyperthreading because they could. Okay. So multiprocessing and multiprogramming, I wanted to make sure we cleared out some of these definitions because now we're getting kind of down the rabbit hole with hyperthreads and multiple cores and whatever. So multiprocessing is typically multiple CPUs going on at once. Multiprogramming is multiple jobs or processes. So notice that multiprogramming does not mean that things are running in parallel. It just means that things are potentially scheduled at the same time. Okay, this is this concurrency versus parallelism thing. Okay? Everybody understood the difference between concurrency and parallelism? Anybody want to recall that? Okay. Everybody remember? Let's see, do I have a picture here? Multiprocessing, they actually happen at the same time. Multiprogramming or concurrency, they can happen, they're all scheduled at the same time and they can be interleaved, but they aren't necessarily processing at exactly the same time. Okay, so concurrency or multiprogramming, which is the one on the bottom, you've already bitten off all of the synchronization overhead of having things run in parallel without actually getting the parallelism out of it. Let me say that again. If you've got those threads, green, pink, fuchsia, and purple, blue, all running potentially interleaved, then you've already got to synchronize things properly and you've already bit off all the trouble. Assuming you get that correct, then going to multiprocessing is easy because they just actually run in parallel. Okay? The one on the bottom is what a traditional operating system has been providing for decades with one processor. Once you get multiple cores, you get something closer to the thing on top, or actually a hybrid of the two, where things are actually interleaved and running in parallel, and who knows what order. Okay? Questions? Now, I do want to stress this point because it's important. The scheduler can run things any way it feels like it. Okay, you got to think of the scheduler when you're writing parallel programs as, the ultimate enemy. Okay, that's the big evil you have to defeat, because the scheduler, if it can run something in a way that will screw your program up, the scheduler will do it. Okay, there's a Murphy's Law of scheduling with parallelism. Okay, if it can go wrong, it will go wrong, and it will do so in a way that completely screws up your results. Okay, and that is because the scheduler is unconstrained on how it interleaves and runs things in parallel. The moment you have threads and processes together that can run in parallel, then you've got possible arbitrary interleavings. And so that basically tells us off the bat that in order to show that something's correct, it's got to be correct by design, not correct by testing. Let me say that again. Once you've got this, the bottom, no longer can you test for correctness. You've got to design for correctness. And what we're going to do in the next several lectures is we're going to talk about synchronization techniques that get you something a lot closer to designing by correctness, designing correctly, so that you won't run into weird synchronization bugs. Do not plan on throwing together synchronizing code and hoping to put enough tests at it that you can make it work, because it won't. In fact, that evil scheduler will figure out how to look exactly like it's doing the right thing until you submit it to the autograder, and then it will not. Okay? All right. Did I make that everybody clear? Are we on the same page here? Okay. You cannot test for correctness. Now, what you can do, by the way, I just in deference to my amazing colleagues I have over in SOTA, you can explore the possible executions down to a few levels of interleaving with the right tools. Okay, and so there are folks up on the 7th floor that what they do is they take parallel executions and they figure out how to go through all the possible interleavings to 1 or 2 or 3 levels of interleavings to see whether there might be some bugs you missed. But that testing is still not going to catch every bug, okay? But it might catch some you missed. So the real thing is you design it to be correct, and then you test the bejeebers out of it and hope that things you missed get caught. Okay. Now we've got kind of this interesting picture of single and multi-threaded processes. So here's a single-threaded process. Here's a multi-threaded process. The only difference is multi-threaded one has more stack and register space, but the code, data, and files are all shared. If we put this on top of a kernel, the system now has a bunch of threads inside of it, some of which are exactly matched with threads up on top and some which may not be. So the kernel can have more threads than the user does, and the user can have more threads than the kernel does. And then the moment we start having multiple processors, then we can have several of these things all running in parallel. Okay? All right. So I wanted to, just before our break, I wanted to close with a little bit of a classification here. We can talk about the number of address spaces. Either there's one or there's many. Okay, so one address space is the way to think about things that basically don't have any memory protection. Many address spaces, you have processes. You can talk about number of threads per address space. One is a traditional process. Many is a standard modern process. And we can classify a bunch of different operating systems in these various quadrants. And it's kind of interesting that the one address space and one thread per address space, that was pretty much things that you gave to individuals in the early days. MS-DOS, early Macintosh. A lot of embedded systems were that way. Okay, and the problem with this is there's no protection and there's no parallelism. Okay, so that's kind of a problem, no concurrency. Now this one and many, traditional Unix basically had many processes but only one thread per process. Over here is kind of modern where you have many threads and many processes. And it is kind of interesting that this one address space but many threads is still kind of a mode that low-powered hardware works in, where everything's pretty much trusted and hopefully correct. And you basically have lots of threads, but you don't have a lot of memory protection. Okay, but those are kind of a dying system almost, because hardware is so cheap now that going over here and getting the advantage of the protection is probably still a good thing, even in a little embedded system like a Martian rover or whatever. And we could actually, there were some amusing things that, fortunately you guys got to miss all this, but there was the whole Windows 95, 98, Windows ME was this big, actually Windows 95 was a big bash that was put on by Microsoft, and there was a lot of music that was written for it, and it was a big commercial thing, and we're going to Windows 95, and yada, yada, yada. And somewhere in the 95 to 98, it was like, we've got real memory protection like the big guys do. And it turned out that they didn't really, because it had to run 16-bit code, and there were ways around all of the protection, and so even though it was supposedly protected, there was plenty of ways to crash it. And so, sometimes I do find when technologists try to put out big ad campaigns to explain things to the real person, sometimes it ends up being almost hilarious. But anyway, any questions on classification? Okay, good. Let's take a break, and we'll come back and talk some more.
When you have one processor with different cores, they all access the same physical memory. And when you have different threads, if we have one thread running on the first core and another on the second, then how can we really synchronize? Does it go to the same physical? Do they have access to the same physical memory in terms of the mappings?
Depends totally on how it's mapped.
Okay.
So the answer is yes, the answer is no.
So if there were two different processes, obviously they would have different, like on these two cores running in parallel, they would have entirely different.
different mappings, yes.
Okay.
Or if it's the same process but different threads, they could both be running on different processors but mapped to the same piece of memory.
Okay. Thanks.
Sure. Time for a question?
Yes.
So you mentioned that when you that lots of network servers map each sort of individual connection as a thread, right?
Right.
But what decides? So are you just going to have like one process with like a million threads? What decides how you split up? How do you split it into processes?
That's totally up to the person that does the design.
Okay.
So it's always a trade-off between security and performance. And then the other problem is people can get carried away with trying to put too many threads for performance, and they end up hurting performance instead.
How could that happen?
Well, because you've got too many things happening in parallel, and the context switch overhead is what you're spending all your time switching, and you're not getting any computing done.
That's better than the alternative, though, with process switching, which has way more overhead.
Not after you get too many threads. You could get so many threads that process, right. Well, if you have the same number of processes and threads, yes.
Yeah.
But, what happens is people start with limiting the number of processes, and then they throw a lot of threads in there, and then pretty soon it's not a big thing.
So there's a perfect balance. I mean, there's usually there's a good balance, depending on the sort of workload pattern. Okay, thanks. Yeah.
All right.
So, I just wanted to remind you that we're in this working our spiral out here. So we started with a bunch of OS concepts, and I've had a couple of interesting people. People have come up and talked to me out of class, and they're like, "Well, I didn't quite catch all of that." How that exactly worked with the client-server relationship you talked about. There was a couple of details I missed. It's okay, right? So the reason we started with the high-level concepts was both to start getting you involved in programming them, and that's kind of what homework 0, 1, 2, 3, 4 is, and to sort of get some of the words in your mind so that when we come back to them, we'll be in good place to really explain them for you. And so I think what's interesting is we've actually covered all of these topics in a loose first pass, and we're kind of working our way out here, and we're dealing with concurrency right now. And concurrency, basically that was the bottom of that slide where you can have arbitrary interleavings, is when things start getting really interesting from a synchronization standpoint, and that's the particular depth angle we're going at right now. But before we go there, I wanted to just say a little bit about 162. So historically, the operating system was kind of one of the most complex pieces of software ever. And it had all of these things: concurrency, synchronization, processes, device drivers, all of that stuff was in the kernel so that the user didn't have to worry about it. It's there. I don't have to deal with it. Now, of course, as you're well aware, today many applications are as complicated or more so than actual operating systems. And, how can we explain this? I think people like to make things that are just more complicated than they can quite understand. That's just kind of where they go. They go right to the edge. That's sort of people's way of doing things. But in all seriousness, I would say that the same reasons that applications have gotten complex are the same reasons that the operating system did. And a lot of the ideas that were in the operating system got moved into the application space. Okay, especially as we went distributed. And we're going to talk more about distributed computing later in the term. But for now, so by basically studying OSs, we also sort of gain a lot of important concepts that are in the application level. And we're going to try to understand, in some sense, how these capabilities, these complex capabilities, are actually implemented on the underlying hardware. And by seeing the same concepts multiple times from different perspectives, hopefully this will help you get a good handle on them. Now, the book has a different perspective, and actually you've got two. You've got a book and a sort of a recommended book. Both of those give different perspectives on things, and so this will help. There's a lot of other resources. So how many people have gone to a blog as part of understanding OSs? Anybody gone to a blog? Anybody gone to random opinion pages by people that don't know what they're talking about? Yeah, I do that all the time. It's fun. I write a few of them myself. Anybody? So those resources, you gotta use them wisely. But there are many resources, and there's many very intelligent people out there that have different perspectives on things, and they're great to use. Go for it. Okay, I'm a big fan of using the resources available because let's face it, when you go out into the real world, nobody would claim this is the real world, you're going to use every resource available to you to do a good job and build software that really works. So get used to it now. Okay, and we've got man pages, we've got Google, we've got reference menus, we've got all sorts of stuff. Okay, and basically, part of the philosophy of this newer version of the class, and this is the second time we've taught this, by the way, for those of you that weren't aware of it this way, is that basically the homework project sections are all giving you hands-on detail down to actual code and so on that runs on real hardware, potentially, as a way of getting a good handle on how things work. So when you get stuck in the details and in the weeds, every now and then, or more frequently than that, take a deep breath, come back up, and try to grab a big picture, because I'll tell you, it's very easy to get stuck in the weeds in some of this stuff, okay? So when you find yourself trying to build a synchronization module and you tearing your hair out, and by the way, I've done that a few times, you gotta be able to come back out, try to find a little more perspective, get a high-level view. Don't get stuck permanently down in the weeds or you'll get in trouble, okay? So let's talk about what we're doing now. So we've been basically talking about this narrow waist, the system call interface between user and system. You've spent your first couple of weeks in this class up here, and now with the project, it's time to go down into here. So we're diving below that user system boundary, and this is PinTOS, which, by the way, is a toy operating system developed at Stanford specifically to learn something about. We used to use an operating system called Nachos, which has had several incarnations. The first version of Nachos was written in C++. The second one was in Java. PinTOS is in what language? C? Okay, well, that's good, that's bad. I guess I think this is going to be good because you get to finally take that whole pointer thing by the horns and deal. That's the one thing that C has got, unfortunately, about it. But what we're going to be able to do is we're going to run a real operating system in an emulated environment so that you can actually run it and hope to recover from errors. But by the way, you should know that PinTOS can actually run natively on hardware. Okay, so while you're busy running this in an emulated environment, keep in mind that what you are putting together is something that can actually run on real hardware. Okay, now our groups are almost formed, so that'll be good. We're going to work together as one on these projects. It's very easy when you do projects in a class like this to split it all up. You say, oh, okay, well, you do section 1, you do section 2, you do section 3, you do section 4. Never works. Okay, why is that? Well, because section 1 doesn't work well with section 2, and section 2 doesn't work well with section 3. So the students go away and they come back and they try to put the pieces together, and it just doesn't work that way. Okay, and so we actually have a series of design. We have 2 design processes for this class for each project, which will work your way through a succession of designs and make sure that you've got a higher level idea. And I'm actually going to probably try to fit in a lecture on how to work in a group, because how many people have worked in project groups before? Okay, anybody not worked in a project group before? Ooh, okay. A couple of you. How many people have had 100% successful project group experience? Uh-huh. Oh, one person in the back. Okay, good. I'm going to send everybody up to you. So we'll talk a little bit about group dynamics. I want to say, by the way, that going into the project can be challenging, okay? The reason you've got 4 people in a project is this is more complicated than homework. You've got more time to do it, more people. Keep that in mind, okay? You've got to read a lot of code. You've got to write a much smaller amount of code, but it's more code than for the homework. So just keep that in mind. Don't let it scare you. Just plan for it. Project 1 is going to be on threads in the scheduler. Project 2 is on user processes. There's a project 3, which is going to be in the distributed computing space, but we're not going to talk about that right now. the most important thing is to get started really early. Now, of course, what just happened there is I just said the most important thing is everybody glazed over the moment I said get started early. It was just like, okay? It's much better to get started early and finish early and be relaxing, watching your other colleagues run around like crazy than it is to be running around like crazy with people watching you. Okay? So I wanted to say a little bit about the kernel in PNTOS. Okay, so we actually have a bunch of kernel threads. Okay, and what is a kernel thread in PNTOS? So this is basically kernel space up here with code and data. This is user space with code, data, heaps, etc. And basically, we have a series of kernel threads. This one is running just stuff in the kernel. This one's running as part of this particular user thread. And what's in these various kernel threads? Well, basically there's a thread ID, there's some status, there's a stack pointer, there's some other things, there's a list, which is sort of linking together everybody on the run queue. There's a magic number. Okay, and then the rest of this sucker is for stack. So how big are these? These are actually a 4K chunk of memory per kernel thread. So that 4K chunk has stack plus some stuff. So those kernel stacks are not big. All right, what does that mean? That means that kernel threads cannot compute Fibonacci recursively. Okay, that's a bad idea because there's not enough stack space. Okay, but it is enough stack space to do the kind of things that you do once you enter the kernel. All right, and I will point out, what is this magic number good for? Well, this is so you can have some hope of maybe detecting when your stack is overflowed during debugging, but you can imagine how good that is. Okay, and of course the stack pointer points into this actual page. So this is what a thread kind of looks like in the kernel. And this list sort of links together everybody else that's in the kernel. Okay. Now, the other thing to note is, in addition to the threads, of course, we've actually got register state, which is various things like an instruction pointer, a stack pointer. There's some special kernel stacks that are in the x86 processor that are used to you load them up so that when an interrupt like a timer happens or when a syscall function call happens, the stacks get swapped in. So that's how we make sure that as we make that boundary change from user to kernel, we end up with actually a kernel stack in the right stack pointer. Okay? And it is a feature of modern processors that basically you can set things up so that every entry into the kernel has its own unique stack. And we're never trusting the user's stack, to be correct. So here's an example of some user code where there's an instruction pointer, there's a stack pointer. Its particular kernel thread is actually technically asleep because it's not in use. So it's basically just a structure there waiting for entry into the kernel, but we actually have a pointer to it in the right registers so that when this code might make a system call, the right stack can get swapped in. Okay? So basically these kernel threads are busy executing, so the scheduler is basically selecting from one thread to the next and switching its way through, just kind of like what we just did earlier, where we sort of switched the stack and the thread to the next one, and so on. This one, maybe this was in the kernel doing a system call, and as a result, we switched to it, and then it came out and started executing at user level. Okay. And so there's something called interrupt return instruction, which restores the user stack and the various other registers as part of what's going on. Okay, so the other thing I will point out is that there's an interrupt vector that's going to be useful. So when an interrupt happens, like what's the most important interrupt for scheduling? Timer. Why is the timer interrupt important?
It guarantees we can always retake control.
That's right. It guarantees we always retake control from the user. So when the timer interrupt goes off, we have to make sure that the kernel stack is properly restored. Now, I will point out one other part of the state that I haven't been talking about here, which is the program level. So when we're 3, we're at user mode. When we hit an interrupt and 0, we're at kernel mode. And then when we restore back, we're back at user level. Okay, so there will also be that part of the state. Okay. Now, let me just say a little bit. So what kind of interrupts can happen? We talk about timer interrupts and etc. There is an interrupt vector, and that interrupt vector says when an interrupt of type X comes in, interrupt to a certain piece of code. Okay, and so that's basically how to get controlled entry into the kernel. So all of these are things that you'll be able to find when you start looking at the code. Now I do want to, and there's lots of interrupt vectors. So now let me just show you a little bit. So here is PINTOS interrupt processing. So we have a hardware interrupt vector. So when each one of these things in the interrupt vector for the x86 points to some instructions that will run, and what actually happens when interrupt 20 happens, whatever that happens to be, it pushes the interrupt number on the kernel stack, and it jumps to a shared wrapper for interrupt entry, which saves all the registers, sets up the kernel environment, and calls the interrupt handler. So notice that every one of these interrupt vectors ends up kind of doing the same thing to do the same entry and exit code, and then eventually calls the interrupt handler that was pushed onto the stack up here. So what we've done is we've taken the fact that the hardware can make every one of these different, and we've kind of said, well, let's just make them all the same to make this a little simpler. Okay? And we already talked a little bit about the stack, but let's take a look here. What happens? So we have an interrupt vector. So the interrupt occurs. The interrupt entry is called. That calls the actual interrupt handler. So a good example might be the timer. We start running that particular interrupt handler. It goes through and does its work. At some point, it dispatches based on the PINTOS interrupt handler, and that might actually be the dispatch calls the timer interrupt. So now by looking at this code, we can see, for instance, that interrupt level 20 was the timer. 20 hex, by the way, so that's 32. Calls up here. Oh, 20 hex is 32 in decimal. And so basically, we go from here on the timer interrupt. It sort of goes to the entry code, does the wrapper that calls interrupt.c, which goes and looks up the interrupt handler and starts running the interrupt. Okay, so by the way, you can read this code. Now, I'm not going to expect you to catch all of these pieces, but gee, this is all the little pieces that we talked about, but it's in real code instead of my little cartoony figures that we've been using. Okay? And so the timer may actually trigger the thread switch. So what happens, that timer code may do a thread tick, and every so many ticks, it's time to switch out a thread. In which case, maybe it calls thread yield. Thread yield actually sets the current thread back to ready and pushes it on the ready list and calls schedule to decide which one is next. This should sound a little familiar from the earlier part of the lecture. Then schedule picks the next thread to run, calls switch threads to change all the registers, sets its status to running, and returns back to the interrupt handler. So notice, remember that little cartoon diagram where we had go down with S, go back up with T, right? What we're talking about is we're going down with S, the timer ticks, we go through thread yield, we schedule a new one, we set the stack up, we pick a new stack, we return back up from the interrupt, and we're into a new thread. Okay, cartoon down, cartoon up, reality. So here's how it looks. All right? Going up, interrupt calls the stub calls the generic handler, the handler calls this interrupt, and that called this timer interrupt, and at some point we called thread yield, which called schedule, and now after doing switch, way down here, what does switch do? Switch changes you from the S context to the T context, all right? So we switch, we return from switch into the new thread, we return from that into the interrupt handler. The interrupt handler acknowledges the IRQ, returns the interrupt exit, causes an interrupt return, which restores the user stack and does a return from that, and poof, we resume some other thread, all because of an interrupt. Okay, now, I see some very worried looks. I didn't catch all that. Professor Kuby, could you go over that again? Not right now. But Breathe deeply. Go back to my little cartoon figure. Basically, what I've just described to you is exactly what's going on here, but this is just the details. Okay, we were running along. The interrupt happened, which became a procedure call into the kernel. That procedure call in the kernel decided it was going to do a yield, which called schedule, which called switch. And then when we switched, changed the stacks, we just returned our way back out. And when we're done, we're in a different thread running. It's exactly what I showed you earlier in the lecture. It's just more detailed. Okay? Okay, yeah, take a deep breath. Not so bad. All right. Now, what's good about this, by the way, is you'll have plenty of time to read code to see all this. I just thought I'd give you a little bit of a map of what you're looking for to start with. Okay? Now, what I want to do for the rest of the lecture is I'm going to start... any questions on this? The questions are fine. I wasn't saying you can't ask questions. Okay. Now, by the way, part of this is a mix of, G, what does x86 do? And G, what does PNTOS do? So you see the marrying of, here's what the hardware does, and here's what the operating system does, and those two kind of fit together because of the way that these wrappers, stubs, and interrupt handlers and interrupt things work. So for instance, the fact that the interrupt handler that eventually gets called in PNTOS dispatches through a separate table, that's kind of part of the way the operating system was designed to run on top of this hardware. The fact that the hardware has a vector that calls a stub, that's more of an x86 thing. So at some point, as you're tracing this code, there's sort of the code that's because of x86, and then there's the PNTOS code because it's PNTOS, and those two kind of match up at some point. Okay? Right? Everything in an operating system has a purpose and a reason. Unfortunately, sometimes those purposes and reasons are either obscure or not particularly well thought out. But PNTOS has been designed from the ground up as a teaching operating system, so it's a lot cleaner than many others you're going to run into. Okay, sometimes people try to do a class like this in Linux. We do that with the advanced class. Here, this is cleaner by many orders of magnitude. Okay, Linux, unfortunately, grew in a very organic way, which makes it an amazingly powerful thing, but also very messy as a teaching vehicle. Okay. Now, before we, let me just give you a little roadmap of where we're going next time. What is the correctness criteria for a system with concurrent threads? So if the dispatcher can schedule the threads in any possible way, then programs must work under all possible circumstances. And can you test for this? No. Okay? How do you know if your program works? Correctness by design. Now, one thing that's kind of interesting is if you ever design something where the threads are not exchanging any information and don't impact anybody at all, there's no shared state, and it's much easier to figure out what's going on because it's deterministic. The output is a deterministic function of the input, and it's not affected by weird other threads. So the independent thread case is kind of one that you like to strive after. Oh, that's easy. Okay, and every program you've probably written to date is like this. No, actually not, if you did parallelism in the 61s. It's reproducible, so when you have a bug, you just run it again. Okay. The scheduling order doesn't matter because that one thread is totally unaffected by other threads. The only thing that happens when you schedule other things on top of it is what? What's the worst that happens with an independent thread if you have a bunch of other things scheduled? Takes longer. Okay? If you have threads that are cooperating, what happens? Shared state between multiple threads. Non-deterministic. Non-reproducible. Okay, non-deterministic and non-reproducible means that bugs are intermittent. And this is your great term for the day to end. These are called Heisenbugs. Okay, these are bugs that when you look at them, they go away. And unfortunately, these are the kind of bugs you're going to run into the operating system all the time. In fact, what typically happens is you say, oh, there's a bug. Doggone it, I know sort of where it is. I'm going to write some printf statements. And the printf statements change the timing enough that suddenly it works. That's a Heisenbug. Okay? You know, is it a wave or a particle? Neither. It's just broken, right? So interactions are really going to complicate debugging quite a bit, all right? But of course, let me just, before we really go away and say, well, we're going to do everything independently, is any program truly independent? And unfortunately, the answer is no, because every program shares the file system, the operating system resources, and so on. So in some sense, threads, by the virtue of running on the operating system, are not independent of one another. Okay? And it is kind of amusing. We often used to talk about an example of an evil C compiler, which modified the files behind your back by inserting errors into the C program unless you inserted debugging code, and then it worked perfectly proper compile. Okay? This actually happened. There was a piece of the C compiler was released that did that. More likely is the debugging statements overrun your stack and screw things up, and that's just life. So anyway, we'll talk a lot more about this and how to deal with it. But we talked about, once again, that processes have two parts, threads and address spaces. We talked about concurrency, many ways of multiplexing the CPU to get concurrency. We talked about protection, restricting access. Okay, that's been a long time topic here. But now we're starting to bring in the fact that concurrent threads are extremely useful abstraction for lots of things. We're going to get a lot more discussion of why they're useful. But there are all sorts of problems with shared data. And by the way, for today, I put up a couple of readings, which I suggest you take a look at next time. Maybe I'll move them to next time, of some specific cases where a concurrent bug actually ended up killing patients in a radiation therapy device. Okay? And another bug, which wasn't quite so devastating, that prevented the original shuttle from taking off. So concurrency basically is the name of the game, and we're going to fix it with atomic operations, and that's our topic for Wednesday. So have a great couple of days. We'll see you on Wednesday. Make sure you've got a group. Make sure you start on Project 1. We'll see you then.